Good afternoon, everyone. Welcome back to the Capella stage. Hope everyone is recharged and ready for this last part. We are happy to proceed with the quantum track. And today we have with us Enrico Bottazzi, the who's gonna present us the quantum research, the of new frontiers in multi-party computation with IO. Enrico is cryptography researcher. It was a new topic. Okay, we have an update, even recent research.
Yeah. So I think the topic is different from the one that I originally proposed. And actually, the topic, as you see from the title, is going to be quantum money plus via indistinguishability obfuscation. So you might have already heard about quantum money during the conference. And today I'm gonna add a new component to that, which is indistinguishability obfuscation, which is a technology that is more classical cryptography. So it's less of quantum cryptography. And we're gonna use it to enhance, to upgrade, add new properties to quantum money. And I work at Machina.io, which is a research team focused on building indistinguishability obfuscation, and this team is part of the Ethereum Foundation. So we are going to start with a brief history of money. We are going to analyze three types of money: cash, Bitcoin, and quantum money. And you notice that I put the quantum money after Bitcoin, even though the construction was published more than 35 years before the quantum money. And that's because even if it came before Bitcoin, it's still way less practical than Bitcoin. And the reason might be, for example, the lack of quantum channels and more importantly, the lack of capacity to preserve the quantum state for enough time. So we're not really gonna analyze each type of money. We're just gonna analyze them through two properties. So one property is the traceability. We define traceability as the capacity for an external actor, for an external party, to keep track of the movement of this money. So, for example, when it comes to cash, we can see from our experience that the traceability is low. Every time you get some cash, some banknote, you cannot really tell who was the previous owner of this cash. When it comes to Bitcoin, the traceability is really high because by design, the blockchain of Bitcoin is public. So you can see every transfer, who transfer what, how much, to whom. And lastly, we say, I'm claiming that the traceability when it comes to quantum money is medium, which kind of contradicts what probably most people would say. Most of the time I see the traceability of quantum money compared to the traceability of cash. So they claim that since it's a sort of like a physical medium of money, it still has no traceability, as similar to cash. But I'm gonna explain you why I believe that this is not true. And this is what we're gonna upgrade using indistinguishability obfuscation. And as the second property, we are gonna analyze the forgeability. And forgeability is the capacity of a malicious actor to clone, to forge, to counterfeit this type of money. And we know that for cash, the forgeability is very easy. Anyone, well, not anyone, but with some effort, is possible to create fake money, to duplicate money. For Bitcoin, it's very hard to forge money. In fact, this is one of the main innovation of the Bitcoin protocol, the capacity to allow for peer-to-peer digital cash that prevents the double spending problem. And this hardness is based on a social consensus. So we know that if there's a 51% attack on Bitcoin, it's possible actually to create infinite copies of Bitcoin. So this is a social hardness, if you want. And lastly, we have the hardness of cloning quantum money, which is still hard, as the same of Bitcoin, but it's a different source of hardness. In this case, the source of hardness is physics. And we are gonna now see what this means. But in general, it's more preferable to have like some hardness based on a physical principle than on some social consensus. So we're gonna now go through the principle of quantum states. You might have already heard of this during this presentation, but I think it's still good to go through that again. So we're gonna divide our algorithms in two. We have the upper part will be dedicated to the quantum state generation algorithm, and later we'll see the measurement algorithm. So for the quantum state generation, we start with a list of bits. So whoever wants to generate this quantum state chooses a list of bits, and this is going to be the information that they want to embed inside this quantum state. As the next step, they're going to flip a coin to generate some randomness, and the result of this coin flip will determine a basis, which is either R or D, where R stands for rectilinear and D stands for diagonal. And the combination between the bit and the basis will determine, the quantum state. So we see that we have 4 possible combinations, and we're gonna analyze them more carefully. So whenever the basis is R, we have 2 possible results, 2 possible qubits, 2 possible quantum states. One state is this arrow that is vertical, and this corresponds to the bit 1 in the rectilinear basis. And we have this horizontal arrow that corresponds to the bit 0 in the rectilinear basis. And next, we have another 2 combinations that appears when we choose the diagonal basis. So we have this 135 degrees inclined arrow for the 1 in the diagonal basis, and we have the 45-degree arrow for bit 0 in the diagonal basis. So really, this is what this sequence of arrows is just like a mathematical notation that we use to represent some quantum state. But really, from the outside, when it comes to measure this, when this sequence of qubits is given to someone, they cannot really see what these arrows or what is the type of information embedded in this quantum state. So what can they do? What can a measurer do when presented with this list of qubits, which we can embed inside the photons, for example? So the measurer will, again, flip the coin, choose a basis, which is either diagonal or rectilinear, and obtain some measurement after this choice. And we see that there are 2 possibilities. So in the case they chose at random the same basis that was chosen by the state generator, they obtain a correct quantum state. So the same arrow, basically, they can obtain. And in the other scenario, and we can also derive a principle from this observation, which is that whenever a quantum state is measured in the correct basis, the measurement yields a correct state. And in the other scenario, whenever the measurer picks a wrong basis, actually the result doesn't match anymore the state that was encoded by the state generator. So we can derive this second principle, that whenever a quantum state is measured in the incorrect basis, because you see that there's a difference between this R and this D, or this D and this R, the measurement yield a randomized, perturbated state. So given these 2, let's say, empirical observation, we can derive a principle, which is the non-cloning principle, that states that someone without the knowledge of the encoded basis cannot obtain, cannot duplicate the original state without disturbance, without injecting some randomness. And this is very cool because it prevents the copying of some quantum state. And we are going to leverage this principle to build some application, such as quantum money. So is it clear? Or okay. So now we are going to use this principle to build quantum money. And first of all, we're going to define a quantum banknote. So a quantum banknote is pretty simple. Like there's a quantum state. So you should really think of a quantum banknote as a physical object that can be exchanged. It won't look like a normal banknote, but it's still something physical. It's not like bits in a computer. It's a physical thing. And it's made of these two components. One quantum state, which is a sequence of qubits. For example, here is 20 qubits. And attached to a serial number, which is the same thing that you see today in normal banknotes. So what's the flow? Like how quantum money are exchanged and who are the subjects that are kind of involved in this exchange? So we have a bank and a set of users. So again, this is very similar to how money are transferred and generated today. And the bank will first generate the quantum state. So they will run the algorithm that we described before, and they will store in their database a mapping between the serial number and the quantum state. This quantum state will be embedded in a banknote, will be created, will be minted, will be passed to some user, and this person is gonna exchange the banknote. For example, they will buy things at the supermarket, pay with this banknote, and then this banknote might end up in the hands of someone else. Again, transfer. And at a certain point, this guy might ask themselves if the banknote that they have in hand is actually legit. Is it valid, or has it been cloned? Has it been generated by some malicious actor? And what they're going to do to verify the legitimacy of this banknote is to go to the bank. They will transfer this banknote to the bank that is going to be able to tell whether this is valid or not. And in this case, we assume a benevolent scenario in which there are no like thief, so the check will pass. But actually, how is this check being performed? So the banknote. So in order to do this verification step, we're gonna leverage the principle that we saw before, especially the one on the top left. Given the fact that the bank has this information in their database, they can actually perform the measurement in the correct basis, and they can obtain the correct state. So in this scenario, they can verify that the state is equal to the one that they generated at mint time that was stored in their database. So in this case, if the banknote wasn't randomized, it wasn't perturbated, the verification will pass. While in the second scenario, in the scenario in which we insert some malicious actor in the schema, what will happen is that the initial process is basically the same. But at a certain moment, this guy, this thief, will try to clone, to duplicate a banknote, and the verification won't pass because the state inside the banknote after this attempt to clone will be modified, and the verification algorithm run from the bank will result in a quantum state that doesn't match the one that they stored in their database. So this is a very cool property, like the capacity, any effort of duplication of cloning will modify the state and therefore somehow naturally invalidate the banknote on a physical level. So this is very cool. And up to now, I've just described quantum money as it was introduced in the original paper in 1983. But now I'm gonna start pointing to the problem, the issue that is inherent in this construction. So the issue is that every time that a user wants to verify the correctness, the legitimacy of a banknote, they need to go back to the bank. And this presents an issue of scalability, meaning that every transfer, basically after every transfer, a user will need to go back to the bank, speak to the bank to verify if this is correct or not. So it's a very bad design, bad system, because every time you need to go back to this central party, and if this party goes online, everything is screwed. So I don't like it as a system. And there's the upgrade, which I define quantum money plus in the title, but technically it's called publicly verifiable quantum money or public key quantum money, allows every user to verify the legitimacy, the correctness of a banknote by themselves. And this seems a bit tricky because the way we described it before was that the verification algorithm was run by the bank because they had access to this database and they could verify a state against this database. And if we were kind of open source, make this database public, this would kind of nullify all the goal of our construction, because this secret information would actually allow the thief to measure the banknote in the correct basis and therefore clone. So we need to create this algorithm that allows this verification, which is based on secret data, but doesn't reveal this secret data. And actually, this is where basically what I'm doing, what I'm studying, comes into place. And this is, in substance, the definition of indistinguishability obfuscation, which again is not a technique based on quantum cryptography, it's based on classical cryptography. So it has nothing to do at its core with quantum physics, but it can be applied to applications such as quantum money. So we're gonna briefly introduce I/O before applying it in the scenario of quantum money. So we start with a simple function. So this is a simple program that performs some arithmetic operation, and this box is transparent, meaning that people can pass their input X, can obtain the output Y, and they can see inside the box what's happening, what this program is doing. And we can think of a similar situation in which someone can feed their input X inside this gray box and get an input Y without really knowing what's inside this box. This box is somehow obfuscated, we say. And this is really the definition of I/O. So I/O, you can think it as a compiler that takes a program, a transparent program, a program definition, and outputs a box, a gray box, an obfuscated box that can be still consumed by people, that maintains the same input and output relation, but it has this very cool property that is able to hide the program definition. And in the case of this arithmetic program, maybe it's not very useful because it's just a very dummy program. You don't want to, there's no reason why you may want to hide what's inside of that. But there are other programs, for example, a signing function, they might have some secret inside. So in this case, the K is the signing key, and the capability of obfuscating this program is able to generate this gray box, this obfuscated box that can be distributed to the public. Everyone can consume it. They don't need to speak with the owner of this signing key, but they can still get a valid output, a correct output. And the coolest thing is that they don't, this box doesn't leak any information about the key. So I think you might have started to understand how this can become useful in the concept of quantum money. And also as a note, if you look into the paper that I mentioned before, is actually a bit more advanced than the way I'm gonna explain it. But the goal here is just to give you an intuition on how I/O can be used to upgrade the quantum money construction. And maybe one other thing that I want to say about indistinguishability obfuscation is that from an interface point of view, there are two main algorithms. Obfuscate algorithm, which is the one that takes as an input a program and outputs the obfuscated version of that. And the second algorithm is the evaluation, which is run by users. It can be run many times and is basically the bottom part of this slide. So the act of passing an input using this obfuscated program and getting an output. Any question on I/O? Okay. So now, finally, we can introduce the concept of quantum plus money. So we compare to the previous flow, we had an initial algorithm which is run at setup time and which is run by the bank. And what the bank is gonna do is they're gonna obfuscate the verification algorithm. So they're gonna obtain this gray box that has the same functionality of the verification algorithm but doesn't really reveal anything. And this is published to the cloud. So every time you see a cloud, this means that this is something that everyone can access. There's no issue in looking what's inside this cloud. Then they're gonna mint their banknotes in the same way they were doing before. And the banknote again can be exchanged freely through users in the market, etc. And the additional point, the difference from the algorithms that we described before is that now the user can really just go to this cloud, which is this abstract actor that is not really permission. They can fetch this gray box and they can evaluate this gray box in the verifier program, passing the bank they receive, and they can obtain this like a thumbs down or thumbs down to tell them if it's valid or not. And in this case, we depicted it in a scenario in which the banknote was forged, but of course this would work the same in the scenario in which the banknote was legitimate. And what really we obtain in this quantum money plus is the capacity to not rely anymore on the bank for the verification. So you can also think a scenario in which the bank will mint all their money and they can later disappear, just go away, and the system will still work. We kind of remove this dependency on the bank throughout the process. So that was the end of my presentation. I just want to conclude what are like the takeaways of our presentation. We saw that quantum money enables a better form of money because of this reliance on physics for unforgeability. But there's some issue, which is this problem of the bank that needs to be present at every verification step. So we added I/O to obtain even better money because we removed this reliance on bank for verification. But probably one thing that is worth mentioning is that like during the conference, we always say that quantum money and in general, like this kind of quantum based cryptography primitives are still far from reality. This is probably less the case for IO, but still IO, like when I go to conferences that are more on classical cryptography, IO is considered not even real, like they think it's kind of a crazy thing. So we are still speaking about two primitives that are very far away in the future. Probably IO is less crazy than quantum money right now, which makes me feel better. So yeah, anyway, we are a Machina IO and we work to make this IO possible, and hopefully whenever quantum money become real, also IO will be real at the time and can enable this quantum plus money. Thank you.